this. And let me share my screen. So welcome everyone to participate in the monthly development cycle of CleanRL. In this week, we are looking at the paper that talks about batch constrained Q-learning. So we'll be sort of delve into it today. This week is a literature week, meaning that we'll sort of read the paper and just discuss how we feel about the paper. And then the following weeks, it's going to be the implementation weeks, and then we will focus more on the implementation. So I guess to start off, does anyone have any particular thoughts on this paper? Any thoughts in terms of if it's difficult to read or things like that?
I just skimmed the paper. I was able to, since we went through the CQL before, I was able to just understand what they are trying to do. On a high level.
Yeah, I feel like this paper, maybe with the actual, I think for me, something that was a little bit challenging to understand was the variational autoencoders, because I wasn't quite aware of that, and when I see in the pseudocode, it just didn't quite make much sense. So I guess for me, I really need to read more on VAE to really understand what's going on in the paper. How about anyone else? Do you find it difficult to understand the source code and that sort of thing? Not source code, but pseudocode.
Yeah, I think if you're not familiar with VAEs, then that bit kind of comes out of nowhere, I guess, or kind of comes in sideways, if you like. It's kind of like, oh yeah, that all makes sense, and then all of a sudden they basically say, we make a variation autoencoder, and then they just give you the kind of the loss function. So I guess if you're familiar with VAEs, it's just like, yeah, great, okay, that makes sense. But if you're not, then that kind of might be a little bit off-putting. But when it comes to coding it up, I don't know if you've probably not had a chance to look at the code, but it's actually not too difficult. Like the VAE part is just like standard VAE stuff. So once you've kind of done the background to VAEs, there's nothing particularly special that they're doing with those. They're just using them as kind of standard. So once you've done the VAE stuff, you'll be much more comfortable with it, I would say.
I see. Yeah, that's great to know. This week I was, go ahead.
Oh, no, sorry, I was just going to say, I think this is one of the first kind of attempts at like a policy constraint method. So things kind of build off this as well, so it's quite good to get to know this one quite well if you can.
Yeah, I agree. It definitely, when I was reading the paper, it definitely felt very different from methods such as CQL. This is going towards a completely new direction. So I guess without further ado, let's just delve into this paper, going for a quick look, and then if at any point you have any questions or anything you would like to discuss, feel free to interrupt me. And then we can talk about it. Also, during the preparation of these slides, I didn't have quite much time, so it was a little sloppy, so I apologize for that. So in the BCQ paper, here's the problem statement. So basically, standard off policy deep reinforcement learning algorithms such as DQ and DDPG are incapable of learning without data correlated to distribution under the current policy, making them ineffective for sort of offline reinforcement learning. To put it more simply, it's saying the distribution under the current policy let's say in the beginning of the training, might be quite focused on the states that are worse than, let's say, the states that are in the state distributions that are in the data set. So it's this mismatch that's causing problem for methods such as DQN or DDPG. So that's sort of the problem. And specifically, this problem of this distribution mismatch is sort of what they refer to as extrapolation error. Let's read the definition a little bit. Extrapolation error is an error in off-policy value learning which is introduced by the mismatch between the data set and the true state action visitation of the current policy. So again, we're talking about the state and action distribution in the data set is a little bit different from the state and action distribution with the current policy. And they talk about various ways that the extrapolation errors can be introduced. So, for example, you have this cause of absent data, meaning that in some cases, the state action pair is not available in the data set, and as a result, the error. So when you do the learning update for DDPG, one of the target you have to estimate the Q value for the next states, and to estimate the Q value for the next states, you need to predict the action of the next states, which is this. But if you don't have data around these data, then this pi of next state could be quite arbitrary, because there's no data of, let's say, pi s prime in the data set. So that might be quite problematic. And that is one of the causes for absent data. Absent data is one of the causes. Did someone want to say something?
Well, as you said, one of the causes might be that the policy might is queried on states that are not necessarily in the data set, probably. And but I think the other aspect of the method is that the extrapolation error. So basically, it's not only the state on the state level, but also with the action. If the state action pairs are not in the data set, then the Q function, the Q value will also be, for example, overestimating because it has never trained on this part of the state distribution. Because it's also not in the data set. So that makes a second one, I guess. I think they wrote it somewhere, but I cannot find the section exact.
Yeah, one quick question though. I thought this S prime would definitely exist in the data set, right? Because when you sample from the replay buffer, it gives you the state action and the next state, which is S prime. What it doesn't give you is the predicted action of S prime, which is this pi S prime. I thought that yeah.
Oh, sorry. I think that when it comes to S prime, the problem is not really actually what is in the data set, but that the policy does not necessarily come across S prime.
I see what you're saying.
S prime during its training. Especially if we compare the policy of an agent at the beginning, while we are trying to have it match some kind of already trained expert. Intuitively, I feel like there is a gap between their state action distribution they induce. So it's like asking someone who is skiing to, I don't know, do some snowboard trick in a sense.
Right. Doing actions on states that the agent has never seen before, and that
Never seen.
Yeah, that could be really bad. So that's one of the potential causes for the extrapolation error. And the second cause according to the paper, is model bias. Specifically, it has something to do with the expectation of the Bellman operator. Basically, I think what the authors are trying to say is, you're really maximizing the Bellman operator over the expectation over the data set rather than the true distribution. So that might also be quite problematic. And the third cause is this training mismatch. Sorry. So let's see. Even with sufficient data, transitions are sampled uniformly from the data set, giving a loss weighted with respect to the likelihood of the data. If the distribution of data in a batch does not correspond with the distribution under the current policy, the value function may be a poor estimate of actions selected by the current policy. I was a little confused about this particular part. Does anyone have like a pretty straightforward interpretation of this?
Yes, I think that was what I was trying to talk about just before. Mainly the problem, to the best of my knowledge, is when evaluating the gamma q phi dash of s dash and pi s dash. Since we train the q value function on the expert data set. But what the policy is encountering, especially at the beginning of the training, for example, is not necessarily present in the expert data set. So while the q theta might be accurate on the expert data set, it actually does not extrapolate on what the agent is currently experiencing. So it gives you a kind of a broken q value function because it was never trained where the agent is exploring, kind of.
I see. Maybe a poor estimate. Yeah, so those are some of the major causes for extrapolation error. So this part was some part I feel like there were some repetitive elements in these reasons, but maybe reading it a little more will help me understand like the absolute difference between them. But what I found really helpful was their empirical experiments to sort of illustrate it. So they basically did a couple of experiments where they are training an offline DDPG and with the behavioral policy, and they have three settings where the offline off policy DDPG is learning from. The first setting is final buffer performance, B is a concurrent performance, and C is imitation performance. So in A, basically they're training a DDPG from scratch, and then it keeps incrementing the replay buffer until the training is finished for 1,000,000 time steps. So they have this buffer that has all these diverse experience from the first time step to the 1,000,000 time steps. And they use this buffer to train the offline DDPG. So the offline DDPG sample from this final buffer, which contains everything from start to finish. And then they use it to train the offline DDPG, which performs pretty well. And then they have this concurrent performance, which they train an offline DDPG and an online DDPG at the same time, and they use the replay buffer of the online DDPG to train the offline DDPG. And lastly, they have this imitation learning setting where they're essentially taking they're generating the replay buffer with an expert, and then they're trying to let the offline DDPG sample from this buffer, and then learn from it. So for me, what's really interesting is the concurrent performance, right? Because the concurrent performance, you're training an online on-policy DDPG and off-policy DDPG at the same time. And so in a sense, they would maybe share some sort of similar progress of training, therefore they should have similar performance, but the results are a little counterintuitive. So the author suggests that even in the concurrent experiments where both agents are trained with the same data set, there is a large gap in the performance in every single trial. So in essence, they're suggesting that the difference in state distributions between their policies is enough for the extrapolation to set the whole thing off. Which I thought was pretty interesting. And for me, what's surprising is that the final buffer performance actually performs really well, even though the buffer is just the sum of experience of the online DDPG. So I thought these are quite interesting. And that's where the authors propose that the off-policy deep reinforcement learning algorithm really suffers because there's a mismatch between the distribution of the current policy and the policy in the data set. So here is the simple idea, which is this purple highlighted line. To avoid extrapolation error, a policy should induce a similar state action visitation to the batch. So which sets up the whole theme for the entire paper. And specifically, they want to select actions with respect to 3 objectives. So the first one is to minimize the distance between the selected actions to data in the batch. And then they also want to lead the states where familiar data can be observed. And lastly, to maximize the value function. The first 2 makes a lot of sense. It's essentially saying, okay, I know I don't have a lot of data, so I want to select actions that are similar to what I have in the data, and I want to go into states that are similar in the data. So I think those 2 points are very intuitive. And it should lead to better performance because then you have data that makes more sense to the algorithm rather than a lot of data that the agent has never seen before. Or sorry, not exists in the data set. So this is the algorithm for BCQ. They initialize the Q network, and this is where things got a little confusing for me. They have this variational encode. So they use the variation autoencoders to sort of generate these actions to be selected from. So they initialize the VAE with some random parameters, the target network. The only thing that's sort of new compared to, let's say, DDPG is probably this VAE components, at least in terms of the initialization phase. And then they sample some mini batches, and then they essentially have a way to update this VAE components, which I'm not quite familiar with. And then they sample n actions sort of using this variation VAE, and then to encourage exploration, I think it's said in the paper, they also perturb the actions a little bit. And then everything else is kind of similar to DDPG. I think over here they have this component where they want to select an action that is perhaps closest to the actions in the data set.
I think it was
yeah.
The file update part.
Mm-hmm.
There is a action plus epsilon.
Let me see what this part is.
I think it was in the algorithm.
Right. So
The I think it's Xi, right? Perturbation network. I
Yeah.
think it could be useful to think of it as just the normal noise we sample to add to the actions in DDPG, for example.
Mm-hmm. Yeah, and I think something that I didn't quite connect with the paper and the formula is where they're saying they want to penalize uncertainty over future states, where they made some modification, I think, to the selection of the Y. Maybe it'll become clearer to me when I dig a little more into it, but right now I'm not quite seeing the connection.
So I think this will all become a lot clearer when you start delving into their code, which I find happens quite a lot with some of this stuff. But yes, essentially what's happening is, so the VAE is trying to mimic the behavior policy, but it's not done using kind of like, I guess, normal supervised. What is VAE supervised learning? It's trying to, it's a variational autoencoder, so it's trying to mimic the behavior policy, but also generate actions that are kind of similar to it, but not exactly the same, because that would kind of defeat the point a bit. And then this perturbation model takes the action from the VAE and then just perturbs it like a little bit, so that the action is similar to the VAE, but also kind of not quite the same, and that's kind of your exploration. And what they kind of say is when you're updating phi, you're kind of discovering the optimal perturbation, if you like, the kind of the perturbation that's not too much but not too little either. So enough so that you are learning a better policy than what's in the behavior in the data set, but not wildly off so that you have the problem of the extrapolation errors. Is kind of the long and short of it, if you like.
I see. That's a really good explanation. Thank you, Alex.
Yeah, I probably wouldn't have got that just from the paper. So you'll see it makes much more sense when you start putting it, copying their code that they've done, which is really nice, by the way, their code. You'll enjoy that.
Nice. Yeah, I really enjoy the papers from this author. So before, in the past, we've done also a monthly development cycle on this author's paper, which is TD3, which some of you probably remember, but it was a really, when we dig into the code, it was very organized and very easy to understand. So I really look forward to this time looking into BCQ as well.
And it's all in one Python file as well. It's not calling from lots of different places.
Nice. I love that.
So yeah, if you've done DDPG, then they kind of use that as the basis for their updating their policy.
I see. That's fantastic to know. I don't have much part after that, but basically they did the experiments again. The final buffer performance. Final buffer setting, imitation setting, concurrent setting. And they also add this new setting where the demonstrations are imperfect, probably a little variation from the imitation. And basically, in all 4 cases, BCQ was able to perform rather well, which to me was, I thought it was pretty amazing, just because it's when you're competing against baselines, when you have such an obvious advantage over the baselines, it usually means your algorithm is very well tuned, but also is very well designed as well.
Yeah, and they later on in the D4RL paper they use BCQ as one of their kind of comparisons. So I think I mentioned it in the chat that this paper came out before D4RL. And so they obviously didn't have those data sets, so they made their own. And then if you go to the appendix, it's got the raw scores rather than the normalized ones. That one there, you need to see it compared to the other
This
ones.
is gonna, I don't know, kill my next or something.
If you right click, I think it should allow you to.
Oh, it allows me. Yeah, there we go.
Yeah, so BCQ is in there with
Over here.
all the other ones that we'll be looking at some point, I imagine. So BEAR is another policy constrained one, as is BRAC.
Okay. Nice. So I guess to start to have some feelings of the performance, have some ideas. I'm just looking at, let's say, half cheetah. Okay, BCQ performs.
Yeah, it doesn't do very well on that one.
Actually,
to be fair, I've managed to get it to do better than that. So maybe they were just unlucky. The problem with the random data sets is they're very unstable. So they might have just had a bit of bad luck when it comes to like initializing the parameters.
Mm-hmm. I see. And over here they have this SAC. Is this with CQL or just SAC by itself?
So that's like the kind of like the online soft actor critic. That's not constrained. The constrained one is the SAC off that's in the.
Oh, I see.
So that basically the SAC is kind of like what you're aiming for, I guess. That's because at half cheetah it's got like 12,000, which is like the maximum score.
Mm-hmm.
Walker 2D is about 4.5, and Hopper is, so they're all kind of what you're aiming for, if you like. That's the expert score, I think.
I see. Yeah. Did they include a CQL here somewhere?
A CQL came out after D4RL.
Oh, never mind. That's kind of a shame. But actually, CQL paper probably has BCQ in it. I forgot that.
The annoying thing with the CQL paper is that they put the normalized scores. So actually, they do normalized scores, so it's a bit harder to get the exact scores. But yeah, it's in this. Apart from in the appendix, they have some normalized, and then in the appendix they have some raw scores.
Mm-hmm. I see.
It's in there somewhere.
Do you guys know, just out of curiosity, where is VAE used like originally? Is it for language task or?
So I think it was used for images before. Maybe I'm not sure. I know GANs.
Yeah.
So they're used a lot for images. I think VAEs were as well at one point. I think actually what's interesting is I think VAEs are used for these new what's it called? I've forgotten the name, but where you're learning a policy in latent action space. So you take your images and you put them in a latent space, and you learn your policy in your latent space. I think that's what it is. Yeah, Dreamer. Yeah, that's the one.
And what does it mean, latent space?
So essentially, what they're trying to do is kind of like a dimensionality reduction thing. So your images may be, say, 78 by whatever, 78 pixels, and then what you're training your variational autoencoder to be able to generate images from like a latent space, where the latent space could be something like, which is much smaller than your original image space.
I see.
So you may, for example, sample, I don't know, like a vector of 50 from a normal distribution, and so your decoder tries to decode that into an image. So essentially, once it's kind of like a dimensionality reduction thing, if you like.
I see. And I kind of remember something when I was looking over PPO's baselines code, but basically they called the value, I don't know if it's related, but they called the sort of layer just before the output layer for the value function, they call it value function latent. So I guess maybe it just might be a term to indicate something in between.
So you have, on the kind of, if you picture your kind of neural network from left to right, on the left hand side you have your image, and then you have a decoder to decode it into a latent space. An encoder decodes it into a latent space, which is in the middle, and then you have a decoder which generates an image on the right hand side of your network. So you've got like three components: image on the left, encoder, latent space in the middle, decoder, a new image that's generated on the right. And you get conditional VAEs as well, which are basically the same thing. It's just that if you just use a VAE, say for like the MNIST data set, you'll just generate random images. You won't be able to control the number you want to generate. But a conditional variation autoencoder lets you choose what image you want to generate. So either loads of ones or loads of nines or something like that.
I see. That's very interesting. Out of curiosity, is VAE sort of a central part of GANs, or is original GAN sort of built without VAE?
No, there are different methods.
Okay.
Yes.
Independent.
Yeah.
Okay.
But they kind of have the same concept and the same objective.
I see. Yeah, I was just thinking.
Also,
yeah.
just to tie back to your OpenAI baseline PPU value function with latent, I am pretty sure that latent is completely different from the VAE one.
I see. Okay.
It probably just means that it's hidden.
Yeah.
Yeah, so there's obviously like the actual meaning. It can get a bit confusing. I think it's a bit confusing because VAEs, like when you're talking about images, are kind of like a dimensionality reduction thing, but actually for the offline reinforcement learning, it's more about constraining actions to be similar to a data set. So they're kind of doing different things, if you like.
I see.
But in a sense, because of the auto-encoding parts of the VAE, I think it fits quite well with the objective of minimizing the difference between the state action distribution of the policy and that of the expert dataset.
Say that again.
Yeah.
Because the VAE reconstructs, so you have some data already and you want to learn a really simplified representation, hence latent representation of the data you have.
I see.
And once you do that, you will be able to reconstruct similar data. So in a sense, if you look at the pseudocode, the variational autoencoder, the decoder part is actually our policy. That's where the actions come from. I think the A tilde. So the decoder is a form of making sure that the actions that will be output are related to what we see in the dataset.
Right.
And to do that, the VAE kind of learned the latent dynamics, like the underlying patterns of the state action distribution of the expert policy from a very high level perspective.
I see.
I think you will get it very quickly if you just look up some VAE codes. It's really not.
I see. Yeah, that'll be great. I look forward to check out VAE. I think it's something that I haven't previously experienced with. I think this will be a great opportunity to check it out.
And it's quite easy to code up as well because they kind of have when you see the bit on the kind of the right hand side where they're minimizing the KL divergence, they're using normal distributions. You don't have to do that, but it makes the loss function much easier to calculate because you're doing like a sample based one as well. So that's why they're using normal distributions there. It just makes things much easier.
I see. Yeah, especially I feel like when you code it up in reinforcement learning, a lot of these things are more of a fundamental idea. So I guess it'll be more straightforward than, let's say, VAE used on image recognition. On GANs, where they're gonna have a lot of boilerplate code around loading data and stuff like that.
Yeah. Like I say, the code is really quite nice. It's very easy to follow.
Nice.
Even if you don't quite understand exactly why it is they've done something, you can tell what they're doing, if you know what I mean. It's like, it's not what is going on here. It's like, oh, they're doing that. They're sampling n actions. So, okay, fine, that makes sense.
I see. Yeah, that's great. Yeah, so I don't have too much other than that. Does anyone have any well, with respect to the paper, does anyone have any thoughts or questions, things to discuss about this paper? This will be a great opportunity.
Well, not really related to the theory, the content of the paper, but I just happened to notice that they use quite older version of Half Cheetah. Well, the Mojoko environments, they're using the V1. And I don't know exactly if they have provided the dataset, I guess probably. But I recall we one time tried to downgrade our Mojoko to run some experiment, and it was not going very well.
Yeah, it does.
Hopefully, we will be able to use the D4RL datasets. I think that should not be too much trouble. Okay.
Yeah, I'd just put it on D4RL rather than creating your own data or using theirs.
Yes.
Yeah.
So I guess the point to pay attention to is to make sure that the environment version matches the original BCQ dataset. Otherwise, it might not work.
That's a problem, though. I think D4RL probably uses a higher version of Mojoko. I'm not exactly sure, but it's very likely.
Yeah, you could just compare your results to what's in the D4RL paper. They basically run BCQ on the new versions, or the kind of the latest versions of the Choco environment.
Oh, nice.
Yeah.
Yeah, go ahead.
No, sorry, I'm done.
Oh, I was just thinking, yeah, so I think D4RL, we should definitely use it just, especially for our offline benchmark, now that we have CQL and BCQ on the plan, so it's probably a good idea to unify some baseline data so that we can compare their performance.
Yeah, I think they tend to do it on 3 or 4 random seeds, then take the average of those, and then those shaded areas are usually like 1 standard deviation or something like that, half a standard deviation.
Yeah. So for example, I see Rosalind already has an offline continuous benchmark. So if we can also add, if we can also add BCQ here, I think it will be a great addition.
One thing to note actually is in the code that they provide, they train the VAE at the same time as the actor and the critic, but you can pre-train the VAE, which is what they do in PLAS, which is the kind of the very similar to this, but the policy is learned in the actual latent action space. So if you wanted to just kind of experiment to see what the difference is, I think I'm going to do the same. I'm going to see if it makes any difference. I imagine that if you train it to begin with, it kind of starts off better, but maybe as you get towards maybe 500,000 updates, which is what they do in this, that it's probably similar, because at that point the VAE is trained, but it might just be interesting to see what difference it makes.
Yeah, it makes a lot of sense. All right.
And then the phi, the capital phi that's in the perturbation model, that's the thing that controls how different you want to be. That's your maximum perturbation, if you like. So the higher you set that, the larger you're letting your actions be from the data set, like the more different for the data set. So I think it's kind of similar to what we saw in CQL. Is like, I guess for the expert data sets, you probably don't want to change the actions that much, but when you're getting to the medium data sets, you might want to if we sort of test it for different values of phi, you
Mm-hmm.
might find that having some actions that are a bit more different to the data set might lead to a better overall score.
I see,
So
I see.
I'd test it for a few values of phi. That's what I would do,
Mm-hmm. That makes sense.
including 0 actually, just to see if it makes any difference.
Right. Oh, by the way, Alex, did you figure out what was wrong with the video recording part?
I did, yes. I don't. Well, I fudged it basically. I managed to get it so that I do get a video on the weights and biases thing. What was happening, which is really weird, is I was doing the wrapper, and it was recording the video, and then it wouldn't upload it, and then I would run it again, and it would record a new video, but it would upload the old one. So I was always kind of one behind. Well, it was really weird, but I managed to figure out how to get the current video to upload. I basically had to reset to load the environment in again. So it's a bit of a fudge, but it at least gets me to have the video that I actually want, rather than the video that was just from the previous run.
I see. Yeah, I was talking I was actually talking with someone about this issue. Basically, somehow with the higher version of Jim, it somehow breaks the video upload for weight and biases.
Okay. Oh, so it's not me then.
Yeah, so did you have the issue where basically the video is sort of like 256 bytes and then just completely black in the weight and biases panel?
Yeah, it's kind of like it looked like it was buffering or loading or something, but it wasn't. It was just broken.
Yeah. So I had Jeff, who is one of the fellow students in Drexel, the same university as I was. So this is essentially his run. He deleted it. But basically that was the same problem as we had, and eventually we figured out it was probably there's a new Gym pull request that suggests so if without this newest pull request, which is 11 days ago, then the videos created would be empty.
Okay.
Yeah, and they haven't updated. If you see the sort of what's new over here, they haven't incorporated the newest changes in the Gym version. So if you're having that issue, maybe give it a try. Just resetting Gym version to 0.17.3, the last. The version before the latest version, and I think it'll probably work.
Yeah, it makes sense because I was not having any problems with like Atari. That was working fine.
Mm-hmm.
Sorry, did you say it was Majoko or Jim? What was the problem?
This is Jim. This is Jim.
Oh, okay.
Okay, maybe not exactly the same thing then, because
Yeah, I've managed to fudge it, basically. It's not ideal, but I get the video that I expect gets uploaded. I can share what I did, but it feels a bit like amateurish. It's just fudging stuff to get it to work.
It happens all the time. We do that all the time.
But yes, thank you for providing that code. That was good. That helped.
Well, I'm glad. So I don't have anything else to say. I do have I guess a little bit something a little bit new with the OpenRL benchmark. So the person I was talking about, Jeff, he was considering contributing more experiments with respect to Progen, and because we're using the default API from the Progen environment, the algorithm runs a lot faster. So before, I was using the Gym interface to create a Progen environment, and the steps per second was around 300 versus using the default API for creating vectorized environment, which is 8,000. So that was at least 10 times speed up. And somehow we're still able to record videos as well, but the video's quality is a little problematic. But this will give us a chance to, I guess in a sense, further finish off what we left off with the phasic policy gradient experiments, which I think will be really nice if we can get them done. But yeah, any thoughts or questions? Oops.
I don't think there's anything else from me.
Okay. Yeah, okay. Then let's probably wrap up a little early then. Sorry? Oh, okay. Yeah, let's probably wrap up a little early. Get everyone to start enjoying their Friday. So for the next week, the next week would be the implementation week. So feel free to check out their official implementation, which is already attached into this paper. And this author, according to my experience, has some of the nicest code that has written. So I'd suggest, give it a try, check it out, and see what you can make of it. And then we'll discuss implementation next week.
Yep, sounds good. I can confirm that the code is really nice.
I can second that.
Yeah, it's lovely.
Nice.
Just compared to other methods that we have looked at.
Nice.
It's a breath of fresh air.
Oh.
Well, I've only done the continuous one, but that was nice.
Mm-hmm. Yeah. Did they have any Atari experiments in BCQ?
I think they're completely on continuous tasks.
Yeah, it would appear so. I just happened to notice there's also like in the source code there's also discrete BCQ, which got me a little curious.
Yes, I haven't tried that yet, so presumably.
Yeah.
I wonder how you can do a VAE over discrete variable like this.
I see. Yeah, that's a good point.
I guess we will have to
Yeah.
end on that cliffhanger.
Yeah, I'd actually be quite interested to check it out because my field of research is more aligned with discrete action space. I'd be very interested to see if they did anything interesting with the discrete action space. So maybe something that I should keep in mind for next week.
Yeah, I might have a look at that as well, actually. Mm-hmm. Just trying to see if they've... I know they had some Atari results in the CQL paper. Do they have anything for BCQ?
Yeah, I just searched the keyword Atari and nothing turns up, so probably at least not in the paper.
No, even in the CQL paper, when they're doing their Atari experiments, they compare it to REM, which is random ensemble mixtures, and quantile regression, DQN. There's no comparison to BCQ.
Right. Mm-hmm.
Wait, could you... what is this page? I think in the appendix B2. The B2 section.
Yeah, I just realized I'm looking at it right now. Here I have a DQN.
Okay. Well,
it might be what I'm looking for.
they say they discretize the action. Okay.
Oh, okay. Then.
So actually, I think there is a graph before or after that with the complete. I think it's before that. The B2 section, and they run DQN on Mujoko tasks, which is quite interesting, to say the least.
Yeah.
Okay, one or two page above, I think. We'll see. No, it's section B2. Yes, almost there. Yes,
Okay.
that one. There is TQN
Oh,
running on virtual.
that's pretty funny.
Oh, fair play for trying.
Yeah.
It even reaches 2000 on half cheetah.
Yeah. Yeah, I wonder if they would do like a BCQ DQN since they have DQN, but I don't know.
Yeah, I wonder. Have to have a look at
I'm
that.
pretty sure the challenge will be to encode discrete actions with the VA.
Mm-hmm. Yeah.
There will probably be a problem of mode collapse because the input is discrete, at least part of it.
Mm-hmm.
But it's better to just check out the code. Further speculation will only confuse us, I think.
Right, for sure. All right. Let's wrap it up then. So thank you everyone for coming. I look forward to talking with you next week.
Likewise.
Thanks, everyone. Cheers.
Thanks. Have a good weekend.
Thank you, everyone. Yeah, have a nice weekend. Bye.
Bye.
Nice weekend. Goodbye.
Bye.
Bye.